Alrighty, welcome back everybody. We are going through the network fundamentals area, the pre-security packet. So high level, we're going to understand how data is divided in smaller pieces and transmitted across the network to another device. As normal, there is a video in front. If you want somebody else to walk you through, the TryHackMe people are great. I'm going to try my best to get through these 6 tasks. So starting off with what are packets in frames. So we already kind of touched base on packets in the previous one. So if we look right here, we have a good, most likely a TCP connection going because it's for file sharing. And packet 1, packet 2, packet 3, they're all in order. And guess what? We get a proper file image of a cat. So breaking it down, packets and frames are small pieces of data that when forming together make a larger piece of information or messages. However, there are two different things in the OSI model. A frame is at layer 2, which is that data link layer, meaning there's no such information as IPs. They say think of it as putting an envelope within an envelope and saying it away. So that's kind of that encapsulation that we reference from the previous lesson. So the first envelope will be the packet that you mail, but once it's opened, the envelope within it still exists and contains the data, which is the frame. Alrighty, so the data is the frame. And this process is called encapsulation. At this stage, it's safe to assume that when we're talking anything about IP addresses, we are talking about packets. So if we mention IP addresses, think of packets. When the encapsulating information is stripped away, we're talking about the frame. So IP addresses, packets. Get all the encapsulated information, rip that away, that's the frame. Alrighty. And packets are an efficient way of communicating data across network devices such as those explained in task 1 because the data is exchanged in small pieces. There is less chance of bottlenecking occurring across the network than large messages being sent at once. All right. So it's going to go into this example where there's 3 packets for the cat to form the final image. All right. And then packets have different structures that are dependent upon the type of packet that's being sent. So networking is full of different standards and protocols that act as a set of rules for how the packet is handled on the device. All right. With billions of devices connected to the internet, things can quickly break down. There's no standardization. Just the nightmare scenario of every company coming up with its own way to encapsulate data and actually send stuff. That's just wrong. All right. I like how it has a framework. All right. So let's continue with our example of the internet protocol. So a packet using this protocol will have a set of headers that contain additional pieces of information to the data that's being sent across the network. So some notable headers is the time to live header, which it sets the expiry timer for the packet to not clog up your network if it never manages to reach a host or escape. That's an interesting way to put that. There's the checksum value in the header. So this provides the integrity checking for protocols such as TCP/IP. If any damages or if any data is changed, this value will be different from what was expected and therefore corrupt. The source address, so that's the IP of the device that the packet is being sent from, so that the data knows where to return it, and the destination address, which is the device's IP that the packet is being sent to, so the data knows where to travel next. So your expiration date, how to prove that it is properly valid and what you actually sent, so the integrity of it, where it's coming from, where's it going to. So what is the name for a piece of data when it does not have IP addressing information? All right. So if we remember what that was, boom, it is a packet. All right. And then what is the name for a piece of data when it does not have IP addressing information? And that's going to be a frame. Okay. So when it, I think I said that wrong actually. When it does have IP address information, that's packet. When it doesn't, it's a frame. So that was way back up here. Boom, talking about what the frame is and whatnot. All right. So we're going to go and look at TCP/IP. So the Transmission Control Protocol and the Internet Protocol, and we're going to talk about the 3-way handshake. All right. So the transmission control protocol, remember, that's how like file sharing and things like that, where they really want a reliable connection that is going to make sure all the data, all the packets, everything are arranged in proper order. So we're gonna see how that actually operates. Okay, so TCP is very similar to the OSI model. Um, it consists of 4 layers and arguably is just a summarized version of the OSI model. So TCP has a model where it's application, transport, internet, and network interface. Alrighty, there's not 7, there's only 4 of them. And very similar to how the OSI model works, information is added at each layer of the TCP model as the packet traverses it. So we're talking about encapsulation, and if it's reversing, it's decapsulation. Decapsulation. English, I swear. All right. So one defined feature of TCP is that it's connection based, which means that TCP must establish a connection between both the client device and a device acting on the server before data is actually sent. All right, that's important. It needs that connection to be established before data gets sent. And because of this, TCP guarantees that any data sent will be received on the other end. And this process is known as the three-way handshake, which we'll get to down here. Alrighty, but still going over high-level stuff. We already talked about the advantages of TCP, so we're not going to go over that again. The TCP packets do have headers. They're added on as part of encapsulation, and this has good amount of data in it. And if you ever use Wireshark or anything like that to see traffic going across the network, you can see these packets with header information such as this, such as the source port. So that's the port that the sender sent the TCP packet from the destination port. So whoever's receiving it, that's the port that's going on. The source IP, the destination IP, the sequence number. So we haven't talked about that yet, but excuse me. When a connection occurs, the first piece of data transmitted is given a random number, and we'll go a little bit more further in a little bit. An acknowledgement number. So after a piece of data has been given a sequence number, the number for the next piece of data in the sequence number, or the next piece of data will have the sequence number plus 1, so that goes in order. All right, they have a diagram and everything, don't worry. The checksum is what is checking the integrity of the actual value that's carrying. So if there's checksum ran on it, and if somebody alters that, then the resulting checksum would be different than what's expected there. All right. Then we have data. So that's a header where the data, the bytes of a file that's being transmitted and stored, and a flag. So this header determines how the packet should be handled by either device during the handshake process. So specific flags will determine specific behaviors, and they'll explain that as well. Now we get to the fun part, which is the three-way handshake. Alrighty. The three-way handshake. If you can get this down, you can now partake in a whole bunch of random, funny networking and kind of cybersecurity related puns and whatnot. It opens up the memes for sure. All right. So there's a couple steps in here. The first one is going to be a SYN. So we have a SYN message, and that's the initial packet that's sent to client during the handshake. And it's used to initiate the connection and synchronize the two devices together. The next type of message is known as a SYN ACK. Alrighty, so this packet is sent by the receiving device, the server, in this case, to acknowledge that synchronization attempt from the client. Alright, so it's saying, hey, I got your SYN and I acknowledge it. Third is an acknowledgement packet known as ACK. So we have SYN, SYN ACK, and then ACK. An acknowledgement packet can be used by either the client or the server to acknowledge that a series of messages or packets have been successfully received. Then we have these other types of messages, so data. So once a connection has been established, data such as bytes of a file is sent via the data message. You have FIN. So this packet is used to cleanly and properly close the connection after it's been complete. And then you have the RST packet, and this abruptly ends all the communication. So this is the last resort, and in case there was a problem during the process. So if it's not working correctly, or if there's not enough resources, it can cut off the connection with the reset package or the reset message right there. So this diagram shows Alice over here and Bob, and they are going to be people communicating with the three-way handshake. So Alice wants to talk to Bob, So she sends a send message. Bob gets it and sends his own send slash act because he's acknowledging it. Then Alice confirms that with her own acknowledgement, saying, "Yes, I got that." So very simplified. We're gonna go over more examples, so don't worry. But getting into initial number sequences and how number sequences tie into this. So any sent data is given a random number sequence and is reconstructed using this number sequence and incrementing it by 1. And both computers must agree on the same number sequence for data to be sent in the correct order, and the order is agreed upon in 3 steps, which was here. So in the send step, the client saying, "Here's my initial sequence number to synchronize with 0." And that's just an example of 0 right now. And the SYNAC says from the server, "Here's my initial sequence number to synchronize with," and he'll say it's 5,000. And he has the acknowledgement, "And I acknowledge your initial sequence number of 0." So then Alice, the client, says, "I acknowledge your initial sequence number of 5,000. Here's some data that is my initial sequence number plus 1." And then this little table kind of explains it. So if we have initial sequence number 0, 1, and 2, the final sequence number, we're just adding 1 onto those. So to close a connection, so first, TCP will close a connection once the device has been determined that the other device has successfully received all of the data. Because TCP reserves system resources on a device, it's a best practice to close TCP connections as soon as possible to not burn through resources. And to initiate the closure of TCP connection, the device will send a FIN packet to the other device. Of course, with TCP, the other device will have to acknowledge this packet. So again, back to the messages are being sent, acknowledgments are being like it's just confirming. All right, the three-way handshake, TCP, everything works off of a lot of confirmations in the form of acknowledgments. So this one, Alice sends the FIN message. Bob acknowledges her FIN message, sends a FIN of his own, and then Alice acknowledges his FIN message with acknowledgement of her own. All right, so it's kind of funny. But let's answer some questions. All right, so what is a header in TCP packet that ensures the integrity of the data? So that's going to be the checksum header. And if you remember when we were talking about headers, all of these guys, so the source port, source IP, destination IP, sequence number, acknowledgement number, checksum data, and flag, those all are part of TCP headers. All right, and provide the order of a normal three-way handshake with each step separated by a comma. So we want that send, comma. Then we're going to send this send slash act, and then we're going to acknowledge that as well with another act. So send act. And then we're going to go through this task 3, which is a practical. So help Alice and Bob communicate by reassembling the TCP handshake in the correct order in the static lab. Attach and then enter all the correct values, and we're going to get a flag at the end of this. So Alice is going to start. She has 3 options. Send, "Can you hear me, Bob?" Fin, "Goodbye," ack, what. Okay, so starting off, she wants that send to establish the connection. So she sends a send. Bob now has a couple things. He can cut off the connection with the reset one and just say, "See you later," end it right there. He can ping her to see what the quality is. And then he could also send a SYNAC, which says, "Yes, I can hear you." It's kind of funny just to see if Bob will actually end this conversation. Oh, no, it won't let me send that packet. So let's go with the SYNAC. So now that he has sent that, she can either send a fail message of a segmentation fault, an ACK message of "okay, great" by herself, or the SYN of x equals 3. We want to acknowledge his SYN, so we're going to hit acknowledge. Next, so we have that initial handshake. We now have the connection, alrighty? That has been established. Now we probably want to actually talk of something of substance, right? So Alice can either say ICMP of 99, SYN, "Yes, I can hear you," because he did say, "Hey, yes, I can hear you," and she can say it again to him, or she can start saying data of cheesecake is on sale. So we're done with the initial back and forth of the three-way handshake. Now we're gonna send some data. Alrighty. So she's letting Bob know that cheesecake's on sale. Bob can either acknowledge it and say, "I hear you," and send repeat of what, like send that again, reset, which is help, which is going to kill it. But he's going to say, I hear you. And now Alice can either continue the conversation with an okay, she can do a fin act to say, hey, I'm all done, or she can send an echo to say retry. We're going to start ending this conversation because we have initiated the connection, we have sent data, the data has been acknowledged. Now we're going to go ahead and roll out this conversation with a fin act. Sweet. He can say received as a send. He can do a wire and say reset connection, or fin act and say yeah me too to properly close out that. Now, you might think it might be done right there. It is not, because there's one last thing to do, which is Alice needs to acknowledge his fin, which is with okay bye. Alrighty. So that was very simplified of the of how TCP operates. It's I think it's funny just to see it be put into the human conversation. If that was a lot, don't worry about it. It will always be around, at least in what I've seen. TCP's around. Okay, the internet operates off of it. Through more and more exposure to it, doing labs like with Wireshark, once you see more data, it it kind of starts to all coalesce and smoothly go through. You can always read through this stuff again, watch other videos if you didn't feel like you grasped what just happened. Like if you did not feel very comfortable during that practical, give it some time, try it again. Or if you want to ask some questions, you're more than welcome to. I'll try my best to answer them. But I really enjoy that exercise, that practical, because it does give just, hey, here's how communication flows through TCP. Moving from TCP onto UDP. So remember, last lesson, we were talking about TCP and UDP. So UDP is that user datagram protocol. And it's just another protocol that's used to communicate between devices. So unlike TCP, UDP is stateless, so it doesn't require the constant connection between the two devices to be sent. So in this example, the three-way handshake does not occur, nor is there any synchronization between the two devices. Remember, we're talking about UDP. Start thinking of video streaming. Okay, somebody's live streaming something, so you're gonna have maybe some inequality. Things may jump, but you're still connected. Like you're still getting traffic and whatnot. So it goes over the advantages and disadvantages of UDP. We already went over this. It's much faster, but it doesn't care if you actually get all the data. You might get data all jargled up. It just keeps going. Um, because of that, the packets from UDP is much more simple. It doesn't have the checksum, okay? So it's not going to verify the integrity of the data. There are some headers that are shared between both of them. So we have that time to live again. So that's the expiration part. The source address, the destination address, so it knows where it's coming from, where it's going to. The source port, destination port, again, which ports are being used, and data. So this diagram um, very simply explains how UDP is. Well, we'll do. Let's see. They just say the process of communication, blah blah blah. Anyway, over connection. But Bob is requesting to talk with Alice, and Alice just starts hammering him back with responses on this is just a day that's going. Alrighty. So it's not as complicated as TCP because it doesn't have as much going on. There's not the verification. There's not the 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 checks. So we don't have the sequence number. We don't have the acknowledgement number. We don't have checksum. Okay. So that's just without those, it's a lot more simple to transmit data. So let's go ahead and answer these questions. So what does the term UDP stand for? We did this last time as well, but user datagram protocol. What type of connection? It is a stateless connection. Boom. Which protocol would you use to transfer a file? So the file you definitely want all your file. You want to make sure that What you download is what you download, what you want intended to download. So that's TCP. And which protocol would you use to have a video call? That's going to be UDP. Okay. Um, this is UDP is just easier to grasp than TCP. I would say both have their advantages. While you're on the internet, your device are going to be using both of them. It's not oh, only use this, never use this. In this day and age, most people on the daily are hopping between them. It just depends what you're actually doing. Task 5. Alrighty, let's go over ports. Okay, so that's something that it was referenced here with source port, destination port. It was referenced also in the UDP with source port and destination port. So we're going to go ahead and just read this, and hopefully I won't bungle my way through it, but perhaps the title by their name, ports are an essential point in which data can be exchanged. Think of a harbor and a port. Ships wishing to dock at the harbor will have to go to a port compatible with the dimensions and the facilities located on the ship. When the ship lines up, it will connect to a port at the harbor. Take, for instance, that a cruise liner cannot dock at a port made for a fishing vessel and vice versa. All right. So these ports enforce what can park and where. If it's not compatible, it can't park there. Networking devices also use ports to enforce strict rules when communicating with one another. When a connection has been established, any data sent or received by a device will be sent through these ports. In computing, ports are a numerical value between 0 and 65,535. That's just what it is, all right? So because ports can range anywhere from 0 and 65,535, there quickly runs the risk of losing track of what application is using what port. In a busy harbor equals chaos, all right? So thankfully, we associate applications, software, and behaviors with a standard set of rules. For example, by enforcing that any web browser data is sent over port 80, software developers can design a web browser such as Google Chrome or Firefox to interpret the data in the same way because they're going through the same rule set, all right? So this means that all web browsers now share in common one rule. Data is sent, or I'm sorry, I phrased that wrong because that's not exactly true. Let me read it correctly so I don't lead y'all astray. This means that all web browsers now share one common rule. Data is sent over port 80. How the browser looks, feels, and is easy to use is up to the designer or the user's decision. While the standard rule for web data is port 80, a few other protocols have been allocated a standard rule. Any port that is within 0 and 1024 is known as a common port. And these are ones that you're just going to see frequently, all right? So it has 6 examples here, and these are good examples. Like 1024, you're not going to remember all those, all right? You can Google that. 65,000, you're definitely not going to know. Like, and they're not even all established. Like, it doesn't work that way. So we're going to go over a few protocols. We're going to give numbers. This is not a test. You don't have to memorize these. However, these are very common ones, and it would do you very well to, over time, be able to know when you're looking at ports. 21 equals FTP, which is File Transfer Protocol. 22 is Secure Shell. 80 is HTTP, which is Hypertext Transfer Protocol, versus 443, which is Hypertext Transfer Protocol Secure. We like HTTPS a lot more than HTTP nowadays, all right? But also, not everything's going to have it because that's just how it is, all right? 445 is SMB, which is your server messaging block, all right? You might see that with printers and things like that. Or RDP, which is 3,389. All right. These are common ports. There's a lot of them. You're not going to memorize everything right away. And it might not make the most of sense, especially if you don't know what these protocols are exactly doing or what their use cases are. But if you're in an environment and let's say your environment supports RDP, but then you might see some traffic on 22 from a secure shell, not from an admin or anything like that. That might be, set off some alarms, things like that. And it's just things over time as you are seeing more traffic or just being in an environment more where you're monitoring traffic, you will begin to pick up on these things. Alrighty. They did give a table of the common ports, which is 1,024 of them. Alrighty. I can't tell you, like, picking a random one and having a quiz. I would not be able to tell you, yeah, 666 on TCP is the Doom software. um, so that's kind of funny, but ports, you can always Google them. There's tons of resources to get you where you need to go with them. Um, all ports follow standards. I'm, I'm trying to figure out the best way to crunch up what this is saying here. So admins can change ports already. It's just then not everyone, like external parties, simply won't know that you're actually doing stuff on a different port. My camera's kind of going all crazy. That's all right. So in this example, running a web server on 8080 instead for 80, that's fine. You can do that. If that's in your infrastructure and that's how everything's routed and everybody, all your devices know about that, cool. But other, like if you install a new application, it's going to assume that 80 is still HTTP, all right, instead for 8080. So you might have to do additional configuration and administration if you want to customize these values. But that's enough of me talking about ports right here. We're going to very quickly do this little practical. So we click on view site, it pops up. We have terminal here and it's running netcat. That's what NC is for. And it says open site attach and connect to the address 8.8.8.8 and do it on port 1234. If I could type, that would be great. And here's a netcat command saying connect to port 8.8.8 or IP address of 8.8.8.8 on port 1234. We'll go ahead and hit connect. And hey, there we go. We have connected. We have this flag. You connected to a port. We're gonna hit submit. And then the next one, it's saying, hey, join the final room of this networking module, which we'll be doing. And that is extending your network. It wants me to terminate the labs. So I want to say I can exit split view. I don't see the red button to terminate any of those. So that's what we're going to do. Hit complete and join us in the next room. So thank you everyone for joining me on that. Congratulations if you followed along. You have now completed packets and frames. We are one module away from, or I guess one lesson away from finishing out this networking area of the pre-security area of TryHackMe. So congratulations, and I'll see you in the next one. All right, bye everyone.